Learning Objective 2.1a of identifying independent and dependent variables will be addressed in the project, not the test. 2.1b, which is evaluate functions given numerical input values, will be on the exam. Here they want you to find f of 4 when f of x is this given function. Notice that f of x here now wants you to put a 4 in the place of an x. So you're going to take the 4 and replace all the x values with that and simplify and see what you get. When you do that, you will get the answer of 15.5. Be careful when you go in here. We're going to do our exponents first, then we multiply, and then we do the adding. 1.2c, evaluate functions given a binomial expression. This time they want us to find g of n plus 2, given the fact that g of x is this particular expression. Again, we're going to replace the x with n plus 2. So the n plus 2 goes here, and it goes in here. When you do that, the setup will look like this. And then you'll need to simplify this. Be incredibly careful. PEMDAS says parentheses, then exponents, then multiply. Do not multiply this 3 through until a second step. First thing you must do is n plus 2 squared. Now, n plus 2 squared does not mean you distribute the 2. It means you repeat n plus 2 2 times. So what you would write is 3 times n plus 2 times n plus 2, and then minus 1. Now on here you're multiplying 3 different terms together. You can choose what you want to do first. You can multiply these two first and then finish through and distribute. Let's actually do that. So when you do this, you're going to get this expression here. Now you're going to have to come in and distribute these two binomials together. So I'm going to multiply these two together and then multiply this. When you do that, you will get this right here. And then we're just going to finish it up by adding up the like terms. And when you do that in standard format, 3n squared is first, plus 12n plus 11, which is our final answer. 2.1d, determine if a relation is a function using the vertical line test or point mapping. So in this scenario here, it says the line x equals 2 is a vertical asymptote to the graph below. Let me highlight for you where the graph is. This right here is actually the graph. And then this is the vertical asymptote. And I'll just put x equals 2 right there. Then we have point A, B, and C are also on the graph. And so let's highlight those. Here's A, B, and C. So basically, the green graph and the 3 blue dots actually are the complete graph we're looking at. Question is, which point could be removed to make the graph a function, and explain why? Knowing that the graph here again is the green and the blue, remember the asymptote is an imaginary line that it approaches but doesn't cross. So as of now, if I were to do the vertical line test, this equation or graph would not be a function. It would fail in one spot. Right here it actually doesn't fail. That crosses just one point. It happens to be the green graph and the blue point, and that's fine. And over here, by the way, vertical line would cross just one point. Where it would fail is this line right here. Here it hits point B and it hits the green graph. So what you'd have to remove is point B. So the reason why to pass the vertical line test, you can only cross at one point, which is what I said right here. 2.1e and 2.4c are combined together. And we're going to piggyback off the same example. But this one here says the line x equals -1 is the vertical asymptote to the graph below, which also includes the points A, B, and C. So let's just highlight those with some colors. So this is what they are actually talking about for the graph. We have the 3 blue points, the green graph. Here's the asymptote this time. Be careful, it's hard. This is the x-axis and that's the y-axis. Make sure you can tell the difference. Here's the point now. If point B were removed, this graph would be a function. Give the domain and the range. So first thing that they're actually doing is they're coming in here and they're saying they're going to remove point B. So it's not there anymore. So based on that, give the domain and the range. So remember, the domain deals with the x's and the range deals with the y's. And I'm going to start with the range first. So the y-axis goes up and down. So as you travel on this graph, going up and down, we see that there's graph completely everywhere up and down. There is no limitation. So the range for this function is going to be all reals. So the y's can be any real number. Now for the x's, or the domain, travel along the x-axis. Now we don't see activity until we hit this point here at point A. By the way, point A is -3 and 2. So let's jot that down. So we don't see activity until point A here. The x value for point A is right there at -3. As you continue, again, we don't see it until after we cross this asymptote. So after we hit -1, we start to see graph activity. So therefore, the domain is going to be, let's talk about the green part first, all the x's greater than -1. So I'll say the x's greater than -1. They are not going to include -1 because -1 is an asymptote, it doesn't cross. Now be careful, the blue and the green is the graph, so that includes this, but this point out here is still sitting there. So for domain purposes, you have to say that x can also be -3. So then we're going to say, and then x can also equal -3, and that's the complete domain. 2.2a, algebraically find an equation of a line given 2 points. So the table gives the enrollment of in public education institutions in the United States in thousands for the fall selected years. So for example, in 1980, it looks like there were 50,335,000 students. So really that's 50 million students. In 2000, about 58 million. In 2003, 61 million, and so forth. Algebraically find a linear equation. Let the independent variable be the number of years after 1970, and use the two ordered pairs from 1980 and 1990. So let's highlight that they want us to use 1980 and 1990 as our two ordered pairs. To find algebraically a linear equation, remember that's y equals mx plus b. Now they stated here that the independent variable is the number of years. The independent one is the one we get to choose, or the x. So the years is the x. The dependent variable, therefore, is enrollment. Now also be careful. They state here that they want us to look at the number of years after 1970. So in 1980, the number of years after 1970 would be 10. 1990, it'd be 20. So make sure to use not 1980 and not 1990, but 10 and 20. And we're going to go ahead and find the equation of the line. First thing we're going to do is find the slope. Remember, slope calculation is rise over run, or change in your y's over your change in your x's. So let's go ahead and do 52,061 minus 50,335. Then I'm going to divide by 20 minus 10. That'll give you 1,726 over 10, which gives us a slope of 172.6. Let's take that slope value that we just found and put it in here for the slope. So now we have y equals 172.6x plus b. So the next step is we need to find the b, or in this case, the y-intercept. To find that, all I need to do is plug in a value for x and y, and I can choose either this first ordered pair or the second. I'm going to use the first one, and let's put in 50,335 here. And I'm going to set that equal to 172.6 times the 10 for x, and then plus b. To solve this, what we're going to have is 50,335 equals 1726 plus b. Subtract 1,726 from both sides, and we're going to get that b equals 48,609. Therefore, we can take this value right here, plug that back in for our b, and then write the final equation for our line, which will end up being y equals 1726.6x plus 48,609 is the final answer. And in this case, remember, X stands for the number of years after 1970, and Y will give us the enrollment in thousands. 2.2b wants us to compute the predicted value in a model. So here we have a model for Camp Jolly. Camp attendance over 5 years is given by this particular quadratic equation, where X is the number of years after 2000. The actual attendance in 2004 was 243 people. They want us to predict the value. So let's predict the value for 2004. That's the number of years after, so therefore we're going to make X equal to 4. All we need to do then is put that into the model, and you're going to have to be careful in your simplification. So the first thing you need to do for simplification is exponents. So do 4 squared first, which is 16. Then do 16 times 9, which is 144. Then come in and do negative 2 times 4 is negative 8, plus 145. When you add this together and simplify, you're going to get 281. 2.2c is determine interpolation or extrapolation. This is in the project, but it's good for us to review now. Given that the data used in 2.2b on Camp Jolly was from 2000 to 2005, so they created their equation using the data between these time periods. Was it considered interpolation or extrapolation when we did the estimate for 2004? How do we know? Given that the data they used was in this time period, and we made a prediction for 2004, 2004 is within this given time period, therefore this was called interpolation. If they had asked us to make a prediction, for example, for 2009, 2009 is outside of this time period, so that would be considered extrapolation. 2.2d says compute the residual for a data point in a model. And I want to start down here with the Camp Jolly example, and then we'll go to the top one here. We're going back to the same Camp Jolly, where it was a 5-year period, and this was our particular equation. And X is the number of years after 2000. The actual attendance in 2004 was 243. They want us to compute the residual. So remember the definition of residual. Residual is observed minus predicted. Now in 2004 they actually observed 243 people were there, so we know this amount. So let's go ahead and fill that in. So for the residual, it's going to be 243 minus the prediction. We did find the prediction on the earlier learning objective, and what we did, remember, was just put in 4 for X. And remember, our prediction was 281. So the prediction goes right here. So I'm going to subtract out 281. When you do that, you're going to get that the residual is negative 38. So what that means is this model right here actually over predicted how many people were going to be there. So it predicted 38 more people than were actually there. Now let's go back to this example. Here's an equation. This is an exponential equation. It looks like it's growth. It can be used to model the population of the United States X years after the 1990 census. If the U.S. population in 2008 was this right here, find the residual for this model. So we're going to use the same definition. Residual, again, is observed minus predicted. So in 2008, this was the actual population. So what we have here is the actual observation. So what I need to do is find the prediction and then subtract it from it. So the prediction is going to be, we're going to find it for 2008, but be careful, it's how many years after 1990. It's going to be 18 years. So I'm going to put that into the equation. When you do that, you're going to get this particular value here. Be careful though, when you type this in, exponents are first and then you multiply. And when we get this value, this right here is the prediction. So for the residual, I'm going to take observed minus predicted. And when you do that, observed minus predicted gives us a negative residual, which you can tell the model predicted a higher population than what we actually saw. 2.2e, you're going to compute the sum of the squared residuals. This will be done solely in the project. 2.2f, interpret the slope in context. It looks like here that we are back about at the college enrollment of the years by enrollment numbers per year. It says here the line of best fit for these data is equal to this particular equation. Now let me highlight one thing. The line of best fit means they actually did a linear regression in the calculator. So that's what this means. What we did earlier is we did find an equation of the line given two ordered pairs. We use these two ordered pairs, which was correct for that. But in this case, they found the best line, and they put all this data in the calculator, and it kicked this back. Now what they want us to do is explain the slope of the equation. Easiest way to do this is to remember that slope is, again, in front of the x, and it means rise over run. So what I'm going to do is rewrite it as rise over run, and the number here is 511.31 over the run of 1, because I can write any whole number as a fraction. Now what was rise and what was run? Well, the rise on slope is y over x, so this is enrollment over years. So I recommend that you write this. It might help you see it better. The easiest way to interpret slope is just to take the number, rewrite it as its fraction, and put the words that it stands for, and then interpret it accordingly. All I need to say is this: for every 1 year increase, the enrollment will go up by 511,000 people. Now be careful as you interpret this. If there's negative or positive signs, it does mean difference. This is every 1 year, and this is a positive number, so it increases the enrollment. If this had been negative, I would say enrollment would decrease. So here's what I would write as my definition for what slope is. For every 1 year increase, enrollment increases by that many thousand people. Now 2.3a, make a scatter plot using a calculator, will also be covered within the project. 2.3b, find an equation of the regression line and the linear correlation using a calculator. So again, we're back to the public education institutions enrollment in thousands for the various years here in the numbers. Here again, find the equation for the line of best fit. So line of best fit means in the calculator do linear regression. Be careful, remember they said the number of years is after 1970. So what we want to do is go to the calculator and type in list 1 and list 2. Before we do that, let's change the years to after 1970. So this would be 10, 20, 28, 30, 31, 32, and 33. So that's going to be my list 1. And then I'm going to type this in as list 2. So remember, go and hit Stat, Edit as your first step to do this. After you have that done, you're going to go back to the calculator, and this time you're going to hit Stat and hit Calc, and you need to choose which calculation to do. You're going to do number 4, which is the linear regress. This one looks like AX plus B. When you do that and hit enter, it's going to kick back the answer, and it's going to show it to you in the A and B format. So it'll kick back A and it'll kick back B. The A value for that, what you're going to write, is the 507.16, then X. And then they have plus, it's 43,992.8 is the equation for the line of best fit. Now in this particular example, we are not asked to find the R or the correlation, but remember, the correlation is the R value that comes back on the calculator also. If we look at 2.3c, estimate linear correlation from the scatter plot. So linear correlation, as I just said, is the R value. Remember, R is between -1 up to 1. It cannot be any lower than -1 or higher than 1. And the raw number itself without the negative sign tells you how strong the correlation is. The negative sign tells you the direction of it. So look at this first example here, determine the correlation. I'm going to draw what I think is the line of best fit that best examples it. Might be there. If you look at that, it's going downward, so the correlation would have to be negative. It's not making a very nice straight line, but it's scattered, so I'm going to say about -0.6 seems reasonable. If we look at letter B, This one's a little more complicated in terms of line of best fit. Do they want me to draw this line or a line right here? There's really not great linear correlation. The correlation on here would be 0 because it's not good. Letter C is going downhill again. I'm going to draw my line of best fit. Much closer than it was for A. It is downhill, so it's negative. Much closer. I'm going to say 0.9 roughly. Letter D, the correlation is going positive this time, and it's pretty strong. I'm going to say it's very close to what C looked like, but I'm going to say 0.85. Seems like a reasonable answer. Now be careful, it does say order the scatter plots below in decreasing order by their correlation. So in decreasing order means the smallest number first, so the first scatter plot would be letter C. The next one that's the next smaller is this one here, which is letter A. The correlation of 0 is next of B, and the last correlation is this one, which is D. So these scatter plots are listed from the smallest correlation to the highest correlation. Keeping in mind, smallest means the most negative number, not that it's 0. 2.3d, explain two elements defined by correlation coefficient in context. Again, we're back to our public education enrollment by various years example here. It says here the correlation coefficient for the line of best fit for this data came back at approximately 0.968. Explain what this value tells you about the relationship between the year and the enrollment. Well, the one thing it tells me is because it is positive, it says as the year goes up, as the years increase, the enrollment also increases. And again, I can tell that because it's a positive number. It means it's sloping upward. The next thing it tells me is this number is very close to 1, so it has a very, very strong linear relationship. So what I got from that is the strength of it and the direction. So keep in mind that that's what it tells you. Those two components are very important. 2.4a is find a growth or decay function, evaluate. We will not have that on the test. 2.4b, define an exponential model's rate and factor. So here we have f of x, which is 3.55 times 1.02 to the x power. Remember, this is our initial starting amount here, so we started with 3.55 something, maybe 3.55 grams of bacteria in a petri dish. This entire number here is called the factor, so it's 1.02. By the way, the number that's in here is greater than 1, so I know this is a growth equation. Now there's two ways you could see that this exponential model will be written. This is the format we're actually seeing right now is the initial starting amount and then the growth or decay factor. Again, the growth or decay factor, in this case it's growth, was 1.02. This factor can be broken down though into this component here so we can get more details. So because this is 1.02, they did 1 plus some rate. What was the rate they did? They added 0.02. So the rate on here is 0.02, which is the same as 2%. 2.4d, determine if a graph's equation is growth or decay. Again, we already touched on this one right here. When it's written in this format right here is written where it's the initial starting amount and then the growth or decay factor. We can tell here that's the factor. If that's greater than 1, it's growth. What's the initial starting amount? It was the 3.55. 2.5a is algebraically find an exponential model, which will not be on the test. 2.5b, find an exponential model with a calculator, which we'll cover in the project. 2.5c, write the half-life equation and evaluate. So what we have here is a major decay product of the isotope molybdenum 99 is TC99M, as its abbreviation. This has a half-life of 6 hours. So that means it cuts in half every 6 hours. To the nearest tenth of a gram, how much of a 100 gram sample will remain after 2 hours and 30 minutes? So it looks like we're starting with 100 grams and then you want to know what's left over after this. Now here it says, show how to solve by making a table and by writing a formula. So let's do the table first, and I'll get that set up. So what we see here is we have time and then grams. So at time 0, when the clock first starts, there's 100 grams of this element. Now after the first half-life happens, how much time has gone by? Well, a half-life is 6 hours, so I'm going to put 6 in there. What's going to happen to the 100? It's going to decay to 50. Let's do another half-life. We're going to have one more half-life come by. That's another 6 hours, so be careful. This goes to 12. This will then cut to 25. If I had to do another half-life, another 6 hours has gone by, so now I'm at 18. This will be to 12.5. Now sometimes you can see your answer in here. They want to know after 2.5 hours how much is left. Unfortunately, 2.5 hours is somewhere in here. What I do know, the answer is going to be somewhere between 100 and 50. So I do need the equation. Remember, the equation for half-life is you're going to have, again, y equals your initial starting amount. We already know the decay factor is 1/2. And then we're going to put whatever time that they have over the actual half-life right here. So if we think about it here, we start with 100 grams of an element. I know the length of the half-life is 6 hours. And then 2 hours and 30 minutes have gone by, so that's the same as 2.5 hours. Now if you go ahead and simplify this, you'll end up getting that there's 74.9 grams remaining, which makes sense that it's somewhere in between here. 2.6a, we're going to algebraically find zeros of a function with roots, factoring, or the quadratic formula. So scenario here, a man steps off a 10-meter diving platform. His height in meters above the water after t seconds is given by this particular equation. So if we were to sketch it, by the way, and put it on some XY graph paper, what's going to happen is you're going to see something like this, where this right here is his starting height of 10. And then our x-axis stands for time, and our y-axis stands for height. So they want to know, predict the height of above the water after 1 second. By the way, this right here would be our water. So after 1 second, how high is he above the ground? All we have to do for that is put 1 in for t. So negative 0.491 squared plus 10. When you simplify that, you're going to get 5.1 meters. Okay. The next part here asks, after how many seconds will he hit the water? So if we look at this on the graph, he's going to hit the water right here. So if you take a look at that, that is called the zero, or the x-intercept of the parabola. So we can find the zeros of a parabola by either factoring or doing the quadratic formula or solving it. So they want to know when the height is 0. So what I'm going to do is come into here and make the height 0. So if that's 0, if I look at this equation, I can actually solve this by doing just basic algebra. The reason I can use basic algebra is I can get t by itself. If there was a t squared and another t, I could not. So to solve this, let's first start by subtracting 10 on both sides, which leaves us with this value. Then I'm going to divide by negative 4.9 on both sides, which will leave me with this value here, which simplifies to 2.0408. Now to simplify and solve, take the square root, which will be plus or minus, by the way. When you do this, time's going to be either plus 1.43 or minus 1.43. Now the minus is right here, which is backwards in time, so the minus doesn't make sense, so I cross that one off and say the answer here is 1.43 seconds. Let's do another example, but this time assume that the equation is this one right here. Negative 16t squared plus 12t plus 10. Again, this is the guy doing his dive, so if we want a visual representation of it, there's the 10, there's the time, there's the height. Now they want us to predict the height above the water after 1 second. It works exactly the same way. I'm just going to put 1 in for t and solve. So when I do that this time, I'm going to get that he's 6 meters up high, so he's probably somewhere, probably about right in there. Now the next question, and how many seconds will he hit the water? Again, remember the water is just the ground in this case, or when is it going to hit here? So on this one, what we're going to do, I want to know when the height is 0, so I'm going to put 0 in for h here, so that becomes this equation. Now, when we have this one set up, we have to be careful. I cannot use basic algebra and solve because t squared and t can never be combined together, so that method is out. I have two options. I can either do factoring or the quadratic formula. Now to factor this, what I would probably first do is pull out a greatest common factor to help me do this. And it looks like there is a greatest common factor amongst all of these values, which would be a negative 2. So I'm going to pull out a negative 2, which will leave me with an 8t squared. And then it becomes a negative 6t because I'm pulling out a negative 2 and a minus 5. Now I'm going to try to factor this. If you're not strong at factoring, I will show you how to use the quadratic formula with it. Now it's just a guess and check method right here. I need to take 8t squared and break it into here and here. Well, the t squared is easy, that's t and t. But the 8 is either a 4 and 2 or an 8 and 1 combo. I'm going to guess that it's 4 and 2, and I'm not sure if I'm right. The next thing I'm going to do is find factors of negative 5, and I put them here and here. What I need to do is multiply these two and these two together and try to get negative 6t. So if I do that, can I put factors of negative 5 here and here such that when I multiply this and add, I get negative 6. It does work. It looks like if we put negative 5 here plus 1 here, let me show you. This is negative 10t, this is plus 4t. Add those together, you get that. Now that it's factored, I need to solve. All you do to solve for the factoring is remember, take the factors and set them equal to 0. I'm going to do that up here in the corner. So it's going to be 4t minus 5 equals 0. If I solve that, it's going to be 4t equals 5, or it'll be t equals 5 over 4. The next one would be 2t plus 1 equals 0. I'm going to subtract 1, divide by 2, so time equals negative 1/2. Again, be realistic. In this thing, time cannot be negative, so this answer gets crossed out. The answer here is going to be 5/4 of a second. That's how you do it with factoring. Now, if you don't remember that, you can always revert to the quadratic formula. Remember, just x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. A is here, b is here, c is here. So let's just substitute that in and simplify, and I'll show you what it looks like. When you do that and set it up accordingly to this, and you simplify, you get negative 12 plus or minus 784 divided by negative 32. Now you can take the square root of 784, and you'll get 28. Now you're going to take this and break into its two pieces. So I'll do negative 12 plus 28 over negative 32, and then negative 12 minus 28 over negative 32. This top one is going to come back to negative 1/2, which doesn't work. The bottom one is going to be 5/4. Now let's do 2.6c, and then we'll come back to b because we need c before we do b. C says write an equation for a falling or throwing object model and evaluate. So a man steps off a 15-meter diving platform. Write an equation for his height after t seconds using this particular formula. We're going to use, it looks like in meters per second squared, so we have the g value. This is g, so that goes into there. So what we're seeing is we need to know the initial height, and this, by the way, is going to be equal to his ending height. And then we need to know the velocity. So as we set this up, it's going to be the ending height is equal to negative 1/2. G in this case is 9.8 t squared. The initial velocity, the key here, he steps off. Velocity is speed with direction. If you step off, there's no speed for that. It's going to be 0t. And then his initial height is plus 15. So simplify this equation, and you're going to get h equals negative 4.9 t squared plus 15. So you do want to simplify these equations. Do not leave this as two separate numbers, combine them together. Now, if we were to make a sketch of this scenario, by the way, this man is going to be at about 15 meters high, so let's say that's 15 meters. If you sketch his parabola, it's going to look something like that. Now, if we look at part B here, they want us to find the max or min algebraically and with a calculator. So use the equation from 2.6c to find the maximum height. The maximum height we see here happens right there. So what you can do is go into your calculator. You're going to type the y equals this equation under the graphing, and then do a graph of the feature. Now remember, we want to find the maximum. So now if you're in the initial standard window, you're not going to be able to see this. So when you hit graph, you're going to have to go to window and adjust the window settings. If you change your maximum for the y to about 20, you'll get a decent window for that. Now after you do that, you want to find the maximum. So remember, what you're going to type is going to be second calc or second trace, and then you select maximum. You then have to do left bound and right bound and guess. When you do that, it'll kick back with an ordered pair. Now be careful, what you're going to get for the ordered pair is going to be that x equals negative 1.45 for e to the negative 6. This is scientific notation, so you have to take the decimal place and move it 6 places to the left. So the actual answer here, the time, is going to be 0.000001454. So this is an incredibly quick jump in order for him to meet his maximum height. And by the way, that's in seconds. Now to find it algebraically, what you can do, you can find the maximum of it. The equation for it is negative b over 2a, and then the y value. So to find the negative b over 2a, what you're going to do is we're going to go back to our particular equation here. We're going to notice that there is no b value, so b on here is 0. So I'm going to type in for b for this is 0. And then 2 over a, the a value is negative 4.9. Well, 0 over negative 4.9 is going to be 0. So therefore, I know that the x value to here is 0. So let's plug that in. So that's going to give me 0 and something for the y. How do you find the y value? Well, I'm going to take the x value of 0, or t value in this case, and put it in here. If you put 0 in for t, this will 0 out plus 15. So the ordered pair is at 0, 15. Therefore, go back to the answer we got with the calculator. This right here, if you think about it, 0.00000 seconds is really just going to be 0. So the best answer for this is actually going to be at 0 seconds if you round this accordingly. 2.6d wants us to find a quadratic model with a calculator. So again, we're back to our public education enrollment numbers by year, and they want us to find the quadratic model for this. Again, x are an independent variable, the number of years after 1970. So remember, what we're going to have to do is change the years to after 1970, so 10, 20, and so forth. For quadratic model, when they want you to find a model, that just means use the calculator. So what we're going to do is we're going to type this in here for list 1 and this for list 2. And then you're going to do that within stat edit. And then when you're ready, you're going to stat calculate. You would then choose the quad regression, and when you do that, it'll kick back the values for A, B, and C, and you can just write the equation accordingly. And here is the model that we would use for quadratic modeling. 2.8a wants us to compare residuals of two models and determine the better model. First question here, Jack used a linear model to predict Hawaii's population growth, while Joan used a quadratic model. Jack argued that his model was better since a graph of the data seemed to lie on the line, but Joan insisted her model was better since it had a lower sum of the squared residuals. Explain who is right. Now it looks as though when Jack did it, he thought that his line crossed many of the points and it looked great. But again, Joan had the lower sum of the squared residuals. The lower sum of the squared residuals always wins over anything. You cannot rely on what the picture says. What the numbers kick back is going to be the right answer. So in this case, it's Joan. Second question, below our graphs are the residuals for the linear and the quadratic model. Now be careful, these are a graph of the residuals. It says here, discuss what they tell you about the appropriateness for each model. So right here you're going to notice this is a picture of all the error or the residuals of the linear graph. It's very tight to the x-axis, which is good, and it doesn't really show a pattern. For the quadratic model they chose, this is a picture of the error. We're going to notice it starts to spread out quite a bit in here. It's not very tight, and it kind of shows this parabolic shape. This is not good. So what this tells me is that the linear model is the better model to choose over the two based on the residual plots, because we are looking for no patterns and we want the data to be close to the x-axis.